So welcome again back to SPAAM. We only have one speaker this week, but we're very lucky to have Yiming, who will be talking about crowd counting. Yeah, so thank you very much.
Okay, thank you, Jack, for the introduction. I feel very honored to have the privilege to enjoy the whole seminar myself. Okay, hello everyone. I'm Yiming, a second-year PhD student, doing research in the crowd counting area. That's a sub-area in computer vision. And hope you are doing well in this afternoon. Don't worry, today's talk is going to be a very basic level introduction to crowd counting. Sorry, just give me a second. I think it got frozen. Oh, is everything working? Okay, so first of all, let's have a short review of what crowd counting is about. So given an image with a height, width, and number of channels C. So usually for an RGB image, the C usually equals to 3. Crowd counting aims to automatically estimate the number of people shown in the image. For people familiar with deep learning, you may say, well, this problem can already be solved by object detection. But using object detection can have some disadvantages. That is, it's very difficult to do the box annotations, and this process can be very time-consuming. If you take a look at this image if you take a look at this image for example, oh, what's going on here? It's quite strange. Okay, it's super crowded in this scene, and there are more than 1,000 people shown in this image, and doing box annotation can be very, very difficult. Okay, so the state-of-the-art approaches they're based on some structures resembling autoencoder. They already have an encoder to extract features and a decoder to generate the density maps. Although the ultimate goal is due to correctly predict the total count of people in that image, but they generate the density map instead to take into consider the distribution of the crowd, and the models trained under this scheme can be more robust. So the density map, the ground truth density map is defined by this. That's a matrix, a binary matrix, have the same spatial size. And the value is 1 if the corresponding pixel is a person's head center, otherwise it's 0. So although the image is quite large, although we can have a lot of people shown in the image, but if we just take a count of the head centers, then the matrix is going to be very sparse. Okay, so to obtain the final count, we can simply just add over the matrix, and by a simple use of the triangular inequality here, we know the difference between the total counts can be bounded by the L1 norm of the density maps. Yeah, go ahead.
Find the output of the decoder, or is it the actual?
Yeah, that's the output of the decoder. Yeah. So this is a typical example of how the crowd counting. Sorry, what's going on here? It's very annoying. Okay, I'll do it from here. So this is a very typical example of how crowd counting data set may look like. So on the left-hand side, that's an image of the crowd. And on the right-hand side, you can see there are some pink dots on people's heads. That's the density maps indicating the head centers. Well, for the schemes of crowd countings, most approaches, just as I said, they are based on autoencoder structures. For the training loss functions, traditionally people can use like MSE, or mean squared error or mean absolute error between density maps. But just as I said, the density maps are very sparse, extremely sparse. So training in practice can be very, very difficult. So as a result, people usually use Gaussian kernels to smooth the density maps. But to have a better interpretation, the density maps actually, after smoothing, they actually stand for the probability of the distribution of the head. So the kernel width should be chosen to correspond to the head sizes in the images. And as you can see, people nearer to the camera, they appear to be larger than those in the background. So we should use adaptive kernel width for the smoothing. But this just brings about another problem. How do we choose the kernel width correctly? So therefore, there have been more advanced loss functions that are based on statistical distributions that tries to avoid this Gaussian smoothing. And some of them are based on the Wasserstein distance. And if I have a chance, I will introduce about it in the next talk, maybe. Okay, so that's how people usually deal with crowd counting. And the major problem in crowd counting they try to solve is the scale variation issue. That's just as I said before, people have different sizes in the image. So this issue, I think it can already be well solved by choosing the scale adaptively. You know, in the autoencoder structure, for the features the encoder extracted, they can use some self-attention. Different receptive field sizes based on the people's sizes in the image. So it's not very interesting. So people have turned, researchers in this area, they are going to focus more on other things like multimodalities. So some are trying to also include the depth modality. The depth modality is about the distance between the cross and the camera. So as a result, it can provide some geometry information. And this is very important in crowd counting because it can provide some information about the scene itself. So here is some illustrations about the dataset. And the images below, on the second row are the density, are the depth maps. And just as I said, the depth value corresponds to the distance between the camera and the people's locations. It's the horizontal distance. So if we just make a very simple assumption that people in the world, they all have approximately similar head sizes, then we can simply use the similarity between the two triangles. And to get this equation, here the the lowercase r is people's head sizes or the radius of people's height on the image. And the uppercase r here is people's actual head sizes. And if we just regard it as a constant, then we know the head sizes or the radius of people's height in the image is inversely proportional to the depth value. So if we know that, then we can choose the correct width for Gaussian kernels to smooth the ground truth density map. Or we can also generate the bounding boxes so that we can also perform object detection on this task. But that sounds very ideal, but there is a problem that is, there is really some limitation about the hardware, that is the camera cannot capture people really far away. So here is the illustration. As you can see, there are some people standing near the green taxi on the upper left corner. But in the depth map, the actual values are 0. So that's the limitation of the hardware. So it's not very ideal. So people are trying to abandon the depth modality and they go to the thermal modality instead. The thermal modality can reflect the temperature of the environment. You know, usually the body temperature of people is usually higher than the air. So it's quite obvious in the images. And also the thermal modality is robust to illumination. And for example, if you take a look at this image here, it's very dark. You don't know what's going on inside, right? But if you put on the night vision goggles, you can see there is a special troop hidden in the jungle. But there is some problems regarding the thermal modality. That is, some other devices can also generate heat, and especially in the case when the objects have approximately the same shape of human shapes. For example, pillars. Models may be confused between the actual objects and the cross. So that means we cannot only rely on the thermal modality, we also need to include the RGB modality to avoid these false positives. And for modality fusion, usually we can do one-stage fusion, like early fusion or late fusion. In this case, in the crowd counting case, if we do late fusion, then we generate the density maps independently from each modality, and then we can just simply add them together. But state-of-the-art methods, they fuse the modalities in a hierarchical structure. That means they fuse the features multiple times so that the learned features from each branch can be more robust. People also tend to do the crowd counting from multiple views. Just as I said, there may be some occlusion in the single view. Here is an image taken as the Times Square, and here is a bridge, pedestrian bridge. From this camera, you don't know what's going on under the bridge. You don't know what's going on at the side of the street. But if you can have multiple cameras deployed from different angles, then you can capture the scene from a larger view. And also for one camera, you don't know what's going on when the for those in the background or those really far away from the camera. If we can deploy the camera from here or here, then we can capture the cross behavior better. These are some illustration about the data set. I think it's very interesting. Like to monitor this junction here, they deployed several different cameras from different angles. And the ultimate goal is to match the crowd density from the overview, the bird eye view. And usually they presume that the parameters of the camera are known. So there is some imaging principle, and they can do the projection from the camera view to the ground plane view via some fixed projection. Okay, so basically, that's a very short introduction or overview to the most interesting problems in crowd counting. Any questions or advice? Yep. Thank you very much, Ricky.